Hello, let's talk about transparency. This one. So this is a problem me and Gwiggly made for all future Noah's Arch members. Brownie and Gwiggly are interested in formulating a basis of colors that can span all of the RGBA space. So that's the color space. Basis of RGB is trivial. You can imagine 100, 010, 001. You can add them up, you can get any other color. However, they encountered a problem with the alpha basis. You cannot add two transparencies. I can show that right now. So if I have this transparent rectangle and I put one on top of another, you can see that the middle part is not completely opaque or transparent. The alpha values got like they underwent something, and it looks like it's around 75% opaque right now, right? So this is 50% opaque, and the middle part after putting in 2 is 75%. If I put in another one, it's like 87.5% opaque. I might be wrong, spectacle might work differently, but that's how we're gonna think about this problem. The more you put, the more opaque it becomes. So yeah, you cannot add two transparencies. We will only focus on the alpha value. So for all alpha values a between 0 and n. 0 means completely opaque, n means completely transparent. If you overlap two colors, the transparency ratios get multiplied. So you can think of this as two colors with transparency 0.5 and 0.6. If you multiply them, you get a transparency ratio of 0.3. This operation is valid only if the resultant alpha is an integer. So yeah, that's pretty important. You cannot combine, like, let's say 15 and 16 over 30, like n equals 30 and you combine 15 and 16, you're not going to get an integer. Basically this operation can be summed up as if you have two alpha values a and b, then you get a new alpha value c, which is equals to ab over n for some fixed n. Okay, so n must divide ab, which is not the case for n equals 30 and ab equals 15 and 16. Wait, it is the case, my bad. 15 and 17, there you go. So you cannot combine two colors if the result is not an integer. So yeah, in other words, overlapping alphas w and x, and then overlapping the result with y leads to the alpha z, where z over n is equals to w times x over n times y over n, assuming z and w times x over n are integers. So first you're combining x and w to get wx over n, which must be an integer, and then you're combining this with y to get wx over n times y over n, and this is equals to z. And of course, since it's z over n, it's set to this, it's just z over n, and you can imagine there's like another n somewhere here, so it's w over n, x over n, y over n. The transparency ratios got multiplied here to result in z over n, which is the final transparency ratio for z. So here's the example: n equals to 55, the regular 8-bit maximum. You can generate the alpha 12 by overlapping these four values. Note that you cannot combine 102, 170, and 85 one by one, because if you do that, you won't get an integer. You need to combine them in pairs, 102 with 170, and then 85 and 135. You get two integer alphas, you combine them, and you get 12. So can you formulate the minimum set of alphas they need to get all alphas? You can overlap the same color multiple times. So this is an example. Input 15, you just need these 10 values to get the remaining 5, which are 2, 3, 4, 6, and 8. You can get them from these values. Like 8 you can get from 12 and 10, maybe. Let me try that. 12 times 10 by 15. Yes, I was right. and then 6, and all other ones you can get as well. So 60, you can get every number from this basis. So how do we solve this? So there's two versions. N is capped at 5000 for the small version. The difficulty of that is around 1400. For the harder version, it's around N is capped at 5 million. Time limit is 3 seconds. Memory limit 500 megabytes. I would say this is wrong. I think it's like 1900 right now. And yeah, how do we solve this? So first realize that if you combine two alphas, A and B, so you get C, which is equals to AB over N, right? So we can, since you can overlap only two colors, we can iterate from every, we can set A to be, every color from 1 to N, or 0 to N actually, because 0 is allowed, 0 to N, and B to be every color from 0 to N, and then multiply them, and then, since we can get A and B, then we can get C. Or if we can get A and B, then we can get C. Problem with this is that it says some numbers are constructible. Well, it first of all, it says nothing is, like, everything is constructible. Because if we allow A and B to iterate up to N, then if we want to generate C, what we can do is just set C to be equals to A times N over C times N over N. Right? So set A to be equals to C, set B to be equals to N. And this is true because in this basis, N is like the identity element. If you multiply by N, you always get itself. So you should never try combining with N, because then you will just say that every number is constructible, which is obviously wrong. So yeah, iterate to N minus 1 first of all. And then you might wonder, okay, we say we can combine A and B to get C, but then what if we can combine C with some value D, and then that equals to A. So now A is used to generate C, and C is used to generate A, but that means that neither of them are marked constructible, but in this cycle we need at least one of them to be marked constructible. I mean, marked needed. Both of them are marked constructible, but we need one of them to not be marked constructible, right? Turns out we don't need to worry about that, because since A and B are less than N, when we do the operation C is equals to AB by N, this is less than A or B, because A times B over N is less than A times A over N, N over N, because B is less than N. So C is necessarily less than A, C is necessarily less than B. So if we are saying C is generated by A or B, then C is less than them both. And then we are saying A is generated by C, so A is less than C. C is less than A is less than C. That is a contradiction. So you cannot have cycles. In fact, you can only generate lower numbers from higher numbers. That's what we're getting from here. So from this, you realize that we can kind of go backwards and then generate bases from numbers we know are possible and all that, but not actually necessary. Special values, 0 you cannot construct ever, because to construct 0 you need one of the two numbers to be 0, so that's not gonna happen if you don't put 0 in the basis. N you always need, because as I said, you can only construct lower numbers from higher numbers, and there is no higher alpha than N. So 0 and N always true. If N is prime, well, we'll talk about that later. So let's just write this simple solution for right now for N equals 5000. So that's gonna be colors, take N as input, Then let's go a from 1, a less than n plus plus a, and then same with b. And then let's make an array constructible we set all to true. And then constructible a times b over n is set to false. But this operation is only valid if a times b over n is an integer, so we can write that as if a times b mod n is equals to 0, well, not equals to 0, then continue. And yeah, that should be it. Let's copy this. If constructible I print I let's try this with 15. Yep, works. 60. Yep, works. So does this work fast enough for 5000? Let's try. And that took 0.04 seconds. Does it work fast enough for 5 million? So not fast enough for even 50,000. Yeah, definitely doesn't work for 5 million. So now we have to speed it up. So let's think about it a bit more. We know that ab by n is an integer, right? And we know that a and b are less than n. So this means that the factors of n are spread out amongst a and b. Importantly, this means that n cannot be prime, because if n is prime, then either a or b need to be a multiple of n, because n is prime, for the resultant to be an integer, which means that they must be at least n, which contradicts them being less than n. So n cannot be prime, which means it can be factorized, and since it can be factorized, one of the factors is guaranteed to be at most a square root of n. Is that relevant? Yeah, it is. Anyways, we can factorize n as, let's say, f and n over f, and we can write a as like k times n over f, and b as l times f. So now c, which is equals to ab by n, is k times n over f times l times f over n. And now I can do some cancellations. So ff cancel out, n cancel out. So c is equals to k times l. C is constructible if and only if it is expressed by k times l, where k is between well, a is less than n, right? So this k times n over f is less than n. Divide both sides by n over f, k is less than f. B is also less than n. Divide both sides by f, you get l is less than n over f. So if c is expressible by some numbers k and l such that k is less than f and l is less than n over f, then it's marked not constructible. I mean, it's marked constructible. So how fast is this idea? Well, how many factors f are there of n? Well, that's just the number of divisors function. I'll write that as d of n. And for each of these, you can iterate k from 1 to f minus 1 and l from 1 to n over f minus 1, which is, you have to do it nested, so it's O of f times O of n over f, which is O of n, and the setting it to false is as O of 1, so it's O of n overall, and then the total algorithm time then is O of n times the number of divisors, because for every single divisor f you have to do O of n operations. That's the time complexity of this solution, which is very fast because the number of divisors function is less than any n to the epsilon, where epsilon is greater than 0. So this is nearly O of n. It's still slower than O of n log n, but it's nearly O of, well, n log n. It's slower than any. It's faster than any O of n to the 1 plus e, 1 plus epsilon. So we can code that up. So now this part stays the same. This part changes completely. For int f equals to f less than, or f times f less than n plus f. We don't need to check powers. Well, we don't need to check divisors over the square root of n, because I'll talk about it later. If n mod f equals to, well, not equals to 0, continue, because we only care about divisors. Okay, and then we have to iterate k from 1 to f, and then same with l. It's n over f for this, and for all of them we have to set constructible n k times l to be equals to false, and then that should be it. 30. That looks incorrect. Why is it wrong? Well, that's correct. Oh, I was supposed to do it with 60. Okay, it's correct. And let's see if it works for 5 million. 50,000 first of all, 0.01 seconds, that's nothing. 500,000, 5 million. And yeah, this process takes 1 second. Time limit is 3 seconds, so you can repeat that. In fact, most of the time is actually the output. So if I remove that, now it's 0.2 seconds. But we can actually make this faster, because there is one more optimization that I know of, which is that, okay, I did delete the screenshot, whatever. So k goes from 1 to f minus 1, and l goes from 1 to n over f minus 1, right? Now we are iterating in increasing order of f, that means that n over f decreases, which means that for a lower value of f, we have tested from 1 to f minus 1 with a higher range of L than for a higher value of f, right? So you can imagine for 30, the f can be 2 or 3 or a lot of others f, but let's think about just 2 and 3. So f1 is 2, f2 is 3. So in the case of this 2, we set k to be equals to 1, and then we iterate L from 1 to n over f, which is 15 by minus 1, 14, right? So L we iterate from 1 to 14. For f2, which is 3, we also set k to be equals to 1, and then we iterate from 1 to n over f, which is 10 minus 1, 9. So L is iterated from 1 to 9. So we are setting the same exact numbers to false here. 1 times 1, 1 times 2, up to 1 times 14. We are setting these to false, and then for f2 we are setting up to 1 times 9 to false. We don't need to repeat that work, right? So in fact, for a particular f, all the values from all the values of k before it have already been processed completely, because any higher values will not for any larger f's, n over f will decrease, and we still have to go from 1 to that, which is a smaller range, which is a subset of the current f. So you don't set any new values to false, so you don't actually have to process this at all. So we do not have to process any values under f, so we can start k from f for a particular we can start k from f for the next f. So we can write that down. So let's write that as like k-min. K-min is equals to 1. Start from k-min, and then k-min is equals to f. That's really it. And if we do that and then time it, now it goes from 0.2 seconds to 0.06 seconds. Yeah, and of course it's not that much faster actually, because the output is now what takes the most amount of time. What happened there? Did it not output? Oh, I guess I didn't give it enough time to compile. So yeah, now it takes 0.7 seconds as opposed to 0.9 previously, because 0.7 seconds is spent on outputting. Yeah. Anyways, you can look at the graphs here. Where scale. So this is Gwigly's solution. They all have nearly the same time complexity. I'll talk a little more about them. I believe, yeah, so Gwigly's solution, I believe, is the same time complexity as my unoptimized solution, which was, if you remember, O of n dn. I haven't actually checked through his code, so I don't actually know if that's correct, but I think it's O of n dn. And then if you optimize it, if you do the k-min optimization, it becomes, as you can see, much faster. And time complexity is of course not that much better, but I do believe that there is a new upper bound, which is O of n log n, which I'll talk about in a second. Yeah, do note that Gwigly's solution is not correct here. I don't have his actual correct solution, but I would guess it's around the same amount of time to execute. But they all have roughly the same amount of time complexity. So let's talk about the new O of n log n bound. So if we look at the code now, remember, how did we analyze it previously? Previously, for every factor, which there is d of n of, it took O of n to it took O of n for every single factor, because in the here it was just 1. So this loop, this inner loop, was O of n over f, and the outer loop then is O of f times n over f, which is O of n. And since this runs O of d of n times, it's O of n dn. And of course this part doesn't really affect the time complexity because these are O of n. Yeah. So how do we get a better time complexity? By setting this to be k-min. For every new divisor, so like if we order the divisors f, so f1, f2, and so on to fk, let's say. Now each divisor does not take a constant amount of time to run, right? They run from k-min, which is f of I minus 1. Let's say that it, so for the divisor I, it takes f of I minus f of I minus 1 times O of n over fi, or let's just say n over fi. So now the difference from before is that we have this minus fi term here, which was not here before. What does this do? So now the amount of executions can be written as the sum of fi minus, well, fi minus fi minus 1 fi, and then we can take the n out, so n is here, and this is from I is equals to 1 to n, and fi minus 1 is f0 is 1, let's just say. Okay, so how do we analyze this? You can think of each of these terms as rectangles, okay? So this, if you plot it in a graph, let's say this is f of I minus 1, and this is f of I. So we can plot this as a rectangle, where this is the area, so the height would be 1 over fi. That's the height. Note that the area of this rectangle is less than the area of this curve, right? Because fi is greater than fi minus 1. This curve is 1 over x. That's not right. Is it f? Oh, where did I go wrong? This point needs to touch this curve. This point is 1 over fi. Well, x 1 over fi. Well, x is fi. Oh yeah, so this curve is in fact 1 over x. Yeah. And this area is greater than the area of the rectangle, right? So we can say that fi minus fi minus 1 over fi, this is less than the integral from fi minus 1 to fi of 1 over x dx. And then you can think of this sum as the sums of all these integrals, with these bounds fi minus 1 and fi, which if you do it over all n, then you just get the integral from 1 to n of 1 over x dx. So this is bounded by the integral of 1 over x dx from 1 to n, and we know this is just ln of n. Yeah. So this is an upper bound of O of n log n, yes. So this is better than O of n dn. Of course, there is some values of dn for which dn is much less than log n. So you can think of this bound as O of n min dn log n. And yeah, that's the time complexity of this optimization. You might be wondering, can we get a better bound? And the answer is no, I believe. So, well, the dn part is for specific values, but in general, it's also theta of n log n. Why? Because you can imagine that we have n set to some power of 2, n is some 2 to the k, in which case fi minus 1 by fi is, you can imagine, 2 to the I minus 2 to the I minus 1 by 2 to the I, which is just half, right? So for every divisor, it's this contributes half, which then means that there is how many divisors of 2 to the k are there? Well, 1, 2, 2 squared, up to 2 to the k, right? So every value from 0 to k, that's just log 2 of n divisors. So the best you can do is in fact O of n log n. Yeah, so there's log n divisors, each contribute a constant time. So it's also omega of n log n. So yeah, it's theta of n log n. And yeah, that's the final time complexity of the solution. Let me know if you can do better. Yeah, okay. Expansions. How do we? Well, yeah. How do we continue from here? So there's this restriction here that you can overlap exactly 2 colors. That's because if you allow overlapping more than 2 colors, you can generate sums which are not possible before. Like 21, you can generate as 21 by 30. You can generate it as 25 by 30, 27 by 30, and 28 by 30. And this is simply impossible to do with 2 colors. You can see that the solution yeah, 30. It says that 21 is needed to be in the basis, but you can generate it with 3 colors. So if you allow more than 2 colors, how do you optimize that? You might want to think about that. Also, what if we allow non-integer bases? We also haven't figured that out. I suspect that you cannot do a better set than what you currently can. So first of all, if you do allow non-integer bases, you have infinitely many bases. Why do I say that? Let's say for 15 you have this basis, right? Integer basis. You can take out 14 and put in a value, let's say x, where x is equals to, well, x is equals to the square root of 14 times 15. So this value, if you overlap it with itself, you get square root of 14 times 15 with itself squared by 15, which gets you 14, right? And so if you replace 14 with x, then you can generate 14, and then you can generate everything else. So yeah, you can do that with not just 14, you can replace 14 with any value, any basis, or any non-base, in fact, any integer you want to create, you can generate using this. So let's put it as y, not just integer, any real number you want to generate, you can do it with this. So you can, instead of taking 7, you can do square root of 7 times 15 and then put that there. It works. And you can repeat this, and notably these are all higher. Oh, I should say not any integer except 0 and n, because you cannot generate them otherwise. So this is going to be higher than 14. For any y, this is going to be higher than y. And yeah, so you can always increase it until you get a basis that's like, the basis is like 0 with some numbers, I'll write them as a capital B, where B is in the range n-1 to n. That's very interesting in my opinion. But yeah, you can so the question is, if we allow non-integer bases, can we do with a smaller set of smaller basis set that allows us to create all the integers? So currently there's 10 numbers here. Can we find a basis that can, have less than 10 numbers but be able to construct all the integers regardless? Which I don't believe it, but I do not have a proof for it. So you might want to think about that. Anyways, that's all the questions. I hope you enjoyed this little problem. Hopefully this was not, hopefully this we did originally think of this, this was not copied from somewhere else. I mean, this was not copied from somewhere else. I mean, this was no one else thought of this before. Yeah, that's it, I guess. Thanks for watching, and now you know how to do this, which I'm sure will be very useful in your future life. You're welcome.